Okay, our topic for today is another plot-oriented topic. So this is the third of three special kinds of plots that we're looking at. Up until these three plots, the only plots we knew were kind of concentration versus location plots. But this is the third of the three kind of special plots. The first one was the RFT GFT plot, which would tell us where steady states were in CSTRs. And then Monday we learned the Levenspiel plot, which will help us decide how many reactors we need, what size are they, what order should they come in, what type of reactor are they. And then today we're going to learn our last of the three plots, which is if we want to increase overall conversion by either heating stuff up or cooling it down. This is called Interstage Cooling. It's mentioned in your book in 8.5, so you can see similar pieces of this there. It's the concept that's going to come up on homework problem 7.3. It's also the last concept that's on the blue project statement. So your blue project statement, the last problem is to make a plot that looks like this, which is actually easier than, or at least I think it's easier to do it the way that we do in the project because you've already got the whole MATLAB code sitting there. But there are ways to do it as a shortcut like we're going to learn today. In terms of where we are going, we're almost done. The last topics that we're going to introduce are going to be on Friday and the following Friday, because this Friday we'll start our discussion of rate laws. How do we actually do an experiment to figure out what those are? Monday we don't have class. Wednesday we have another exam. And then if you groan, like, didn't we just have an exam? Yes, we did just have an exam, but now we're going to have another one. The content of the exam on Wednesday goes up to the last bit of CSTRs. So that GFT, RFT stuff, that's the last thing that'll show up on the exam. So nothing today, nothing from Monday, which was the Levenspiel plot, will show up there, just up to that lecture where we had GFT and RFT. That's all that's going to show up. And I just conferred with Jenna, and she said she's going to put another MATLAB coding question on there. So you can thank her for that, and she's giving me that nasty face, because she didn't say that, I said that. But you can blame her if that shows up. That'll be Wednesday. Then when we get to Friday, remember Friday is a video lecture. I'm out of town on Friday, so I will post that video lecture. I will post it as soon as I'm done with it. I won't wait until Friday, but that'll be continuing to talk about the statistical analysis that we need for the topics we'll introduce on Friday. So it'll teach you how to do those analyses in MATLAB. Yeah?
This Friday?
What?
Video lecture.
No, the video lecture is next Friday. This Friday is a normal lecture. Yeah?
Up to what material will midterm 3 be covered?
Midterm 3 just covers up to those GFT, RFT plots.
Okay, so today will be the last day for...
No, that would have been Friday, last Friday. The stuff from Monday, the Levenspiel plot, and this stuff is not on there. Which is basically every reactor we've dealt with previously could show up. So then that next week, we don't have class Monday. We have an exam Wednesday. We technically don't have class Friday because it's a video lecture, so you don't have to show up Monday or Friday to the lecture. And then that gets us into week 10. And week 10 on Monday is Dr. Fenning's guest lecture, which is not going to be recorded. So if you want to see it, you'll have to show up for it. And then Wednesday and Friday, based on the poll results, we're just going to review for the final exam. So I'm going to go over what would I use as my cheat sheet for the final exam. You're going to get 2 pages for that instead of 1. So we'll go over the kind of stuff that I would put on that on Wednesday and Friday. And then that's it. Don't forget that Friday of week 10 is when your project is due. If you haven't started that project, you might want to do that soon. All right, so today's topic, we're going to figure out what this plot means, how do we use it, what is useful about it. Somewhere in your notes, you should have an expression that looks something like this. The conversion of sum species A is equal to the sum of those theta i's, which are the ratios of the inlet flow rates, times Cp of each species, times T minus Ti naught. divided by minus delta H. What kind of reactor was this for? All of them under what condition? Adiabatic. So this was the adiabatic reactor of any style. We saw that we came up with something particularly useful, which is this equation. And since I've mentioned it so many times previously, I feel like it's worth mentioning that we are now finally using this actual equation, which is worth mentioning. Put a little face on here. You got to put a tone. So we're finally going to use this. That second I is a little bit off, but sure, whatever. So we're finally going to make use of this equation because it works for any reactor. Obviously, you are limited to an adiabatic reactor, so this entire discussion in terms of every plot that we make and every conversion that we calculate and every temperature we calculate assumes that the reactor is adiabatic. It does not work if you have a heat exchanger sitting on top of your reactor. But there are a fair number of reactors that are adiabatic. Actually, mostly endothermic reactions tend to be adiabatic for something like this, but exothermics can be done as well. We can do something else if we know a little bit about the reaction. So if we wrote something like A goes to B, reversible A goes to B, with pure A fed. So this is just to make our math easier so that we can see a simple example. It works for anything. So KEQ, which is our equilibrium constant, is going to be equal to Kc, which is C sub B over C sub A. And in terms of conversion, this is the conversion of A over 1 minus the conversion of A. If we calculate that conversion using the KEQ value, this happens to be the equilibrium conversion. So just to distinguish between the two, I'll put the KEQs over here, or sorry, XEQ here, because that's the X we're going to calculate if we only knew that the thing was operating at equilibrium. The other kind of X that we have is this one up here, which we noted was the X we would calculate from solving the energy balance. So I'll superscript that as EB. Conceptually, they're the same X, right? If I'm operating under any given conditions, both of these have to be true. If we wanted to solve for what the actual X was that we were operating at, we would set these two equal to each other so that we could figure it out. So if another way to conceptualize setting these things equal to each other is kind of like the G of T, R of T plot that we saw before. If I plot these two against temperature, I'll get two curves. So I'll draw the equilibrium one in red, since I picked red for that one. So this is what X sub A looks like based on equilibrium. Strictly speaking, that's for an exothermic reaction. The curve switches around if it's for an endothermic. But all the concepts still hold the same for endothermic reactions. And then our energy balance one, what was a very neat function or neat feature of this term that I think I mentioned a few times? It has a particular quality associated with it. It's what? Linear. This is linear. So that delta H that we've got in there, we assumed if that's about constant over all these temperature ranges, we almost always assume that heat capacities are constant. And so the end result is that that function is linear. So we end up getting another line that looks something like this. This is X sub A based on the energy balance. And this intersection point here, the little purple point, purple, fuchsia, I'm going to ask Capes for an extra question and poll you guys to see what color you think that is. This is where the reactor will operate. At the intersection of those two particular points, so we could read off our conversion and our temperature in that particular way. That's the basic idea. We've already solved these problems several times. We've normally done it using MATLAB, so we can just dump it into ODE 45 and it'll figure this information out for us. But there is a graphical approach that looks like this. The advantage of the graphical approach is not so much if we have a single reactor. We know how to do it for a single reactor. The advantage is if we have multiple reactors and we want to increase the conversion. What we have said right now is that for a particular inlet temperature, we are capped at a conversion in A of whatever this value is. Right, I can't get any higher than that. Equilibrium is telling me that under those conditions for that reactor, I can't go any higher than that. So if your process is not profitable under that particular conversion, then you could be in trouble. One way that we get around that is to either heat up or cool down the reactants when they come out of the reactor, and then stick another reactor right after it. This is what we mean when we say interstage cooling and heating. So interstage, inter, not inner. Heating/cooling. It looks somewhat similar to what we saw with the Levenspiel diagrams. Remember, the Levenspiel plots required that you had reactors in series. So there are no side streams coming out of here. We would have an initial reactor up front. The products of that reactor we would send into a heat exchanger. So the symbol for a heat exchanger is a circle with a sort of a lightning bolt through it. The lightning bolt representing energy that's coming out. Heat exchangers can either heat stuff up or cool things down. Just by looking at what those heat exchangers are, we don't know which one it's doing. And then we send the output of that into another reactor. And we can do this as many times as we want. Right, so each one of these are reactors. The way that once you end up seeing process flow diagrams, we abbreviate reactors as R-number, where number is whatever we want. So we have 3 reactors, R1, R2, and R3, and 3 heat exchangers, which are usually abbreviated as HX, sometimes just H. So we've got HX1 and HX2. A key feature of the heat exchangers is that there is no reaction inside a heat exchanger. If there is, you'll tend to damage your heat exchangers. The easiest way to avoid reactions inside a heat exchanger is if a catalyst is needed for your reaction, don't put the catalyst in there. So you don't get any kind of a reaction and you can just change the temperature of them. So this is what an interstage heating cooling system looks like. It's a bunch of reactors, typically packed bed reactors. You could do it with other reactors, but that just tends to be what they look like. Your ammonia project, if you look at the source paper from which that was derived, or any of the kinetics were derived, those are all designed to run that ammonia reaction on a system of reactors with interstage cooling, so that you can jack up the conversion a little bit. So we do actually use something like this. Just like before, we're only interested in the overall conversion here. You can prove that the following analysis works if you do it on a case-by-case basis for, analyzing reactor 1 and then reactor 2 and reactor 3. But the math gets simplified a little bit if you talk about overall conversion. So we're going to imagine that we put a box around this entire system. And that's the overall conversion that we're going to talk about. XA overall is that conversion that we achieve if we look at the first stream, the very first stream that enters the very first reactor, and compare it to the very last stream, the one that comes out of the very last reactor. Keep in mind that overall conversion, you can actually define it anywhere along the way, right? I could define an overall conversion if I were to close that box here, or if I were to close that box here, I can define another overall conversion based on wherever I finish it, but it's always relative to this starting point back here. Right, so when I write that overall conversion, this is always equal to FA in minus FA out over FA in, where I choose this particular value, the FA out. Usually it's the one all the way at the end, but I can resize that box any way that I want to capture any level of those reactors, and I end up with another XA overall. And so we're going to do the following dirty tricks. There's 2 dirty tricks that we're going to do. And as long as you do these tricks exactly this way each time, then this math becomes a lot easier. The following dirty tricks will make this somewhat interesting. Step 1. Calculate XA, EQ, based on inlet conditions. This is the critical point here. When I calculate XAEQ, I'm going to get exactly one curve for XAEQ, and it's going to be based on the inlet to the entire train of reactors. I'm not going to recalculate it for every single reactor. It would actually change for each reactor. Right? If I calculate the XAEQ based on the conditions of this stream over here, all the way at the left, those are not the same equilibrium conditions as I would get over here. Right? At the very least, even if the temperatures were the same, I now have more stuff that's inside there. And so my expression for KEQ is equal to the concentrations of some stuff over another stuff is going to be different. So although they are different, the dirty trick we are employing is we're only going to calculate it once, and it's going to be based on that inlet condition. The second dirty trick that we're going to use is that we're going to calculate XA for the energy balance for the same stream based on inlet conditions. So we're only going to have to do it twice. We're going to analyze any number of reactors by only calculating these things once each. So we're going to have to do 2 calculations. Both of them are based on the inlet condition. As long as we do that, then we can do the following steps. 3 is not really a step, but we're going to use, instead of XA, we're going to talk about XA overall. And we're going to create a plot. I'm going to make this plot kind of big, so you might want to go underneath your code, or your code. Everybody takes notes and codes. So we're going to put temperature here. It's going to look somewhat similar to that one that we just had a moment ago, but instead of XA, we're going to talk about XA overall. If we do these 2 dirty tricks, we're going to first add XAEQ onto this plot, and it's never going to change. Okay, so that is XAEQ. Just remember, it's based on the inlet condition. Now we're going to start adding reactors and heat exchangers based on whatever the diagram is that we saw before. So the diagram that we have in this case is this one. So we're going to go into a reactor, then a heat exchanger, then a reactor, then a heat exchanger, then a reactor. You can do this for as many systems as you want. The line for the energy balance, if I were to solve, let me go back here. Notice this is a linear expression, so I'm just going to make up numbers for that so that we have something to work with. The only dependence that we really need to worry about here is that there is some constant, this, times this quantity T minus Ti naught. So that you're just going to end up with a number times T minus T naught. You're going to know what T naught is as well, because presumably you started off with something like that. So let's say then that for this particular example, we managed to calculate that XAEB is equal to something like 16 times T minus Ti naught. It is probably not going to be the number 16. I'm just looking for a particular number that we haven't seen before so that when I draw 16, we know what we're doing. First reactor, we're going to go over to this plot. We're going to figure out where our inlet temperature is, and we're going to mark that. Let's say we start off here. This is Ti naught. The very first inlet Ti naught. We're going to do exactly the same thing that we would have done for a single reactor, and we're going to plot XAEB is equal to 16 times T minus Ti naught. We're going to figure out where that intersects our equilibrium curve. So we have a line here that has a slope of 16 and an x value of Ti naught, so x being the x-axis. So temperature of Ti naught. What is the corresponding conversion down there at that blue dot? 0, right? We're talking about what has not entered the reactor yet. So our conversion down here is 0. Then we're going to draw a line until it hits the equilibrium curve. The slope of this line is 16. That's what that equation says that's sitting next to us. It's not always going to be 16, obviously. It'll be the slope of whatever your energy balance suggests that it is. This represents reactor 1. You might have enough room on yours to keep writing over next to these numbers, but so that we don't create one of those plots that I've seen before that I already made, I'm going to erase this and just add a tag here that says this is the line that represents reactor 1. We're going to add the next line at the end of the existing line. So what should our slope be if we want to represent a heat exchanger? 0, right? It doesn't change at all. The question then becomes, what's the outlet of the heat exchanger? Usually that's something that's given to you. So for example, if we look back at this setup, let's assume that this is Ti naught. That's the inlet one. And then the heat exchangers are built with sufficient capacity and a nice, clever controller that they always return the streams, no matter what inlet temperature there is to the heat exchanger. They always set the outlet temperature of the heat exchanger back to Ti naught. That doesn't have to be the case. Generally, someone will have to tell you what that temperature is, but let's just assume for the moment that each one of these streams are Ti naught. So no matter what the inlet temperature and conditions are to the heat exchangers are big enough that they always return it back to Ti naught. That's just going to make our plot look a little bit easier. That does not have to be the case. This line then is going to come over horizontally back to Ti naught. If your heat exchanger did not output this to Ti naught, what would you do? Yeah, move it to whatever the new Ti is, right? If it didn't heat it all the way down, maybe it stopped here. That would be okay. You could add your line there. But for this particular example, we've said that our heat exchangers are always going to cool it down to Ti naught, whatever that happens to be. What is the outlet temperature of reactor 1? Where on this plot?
Well, according to this plot, it's got to be lower temperature.
It's got to be what?
A lower temperature.
Lower than?
Lower than what we reached previously with the first reactor.
Well, reactor 1 is already on. So I said, what's the outlet of reactor 1?
Oh, okay.
That dot, right? This intersection that's over here. Let me pick another color. This represents the outlet temperature of reactor 1. Okay, that's a little bit too small. We'll just call it T1. We also now know the overall conversion based on a single reactor. It's whatever this value of x is. Right, so wherever I am here, this is XA overall after going through reactor 1. That happens to be the same as the conversion inside reactor 1. But again, we're only dealing with overall conversions. So now we need to add a line that represents reactor 2. Again, we're going to add it to the end of our previous line. What's the slope going to be?
Whatever number you decide to make up.
Exactly, which is normally calculated how?
What was that?
Which is normally calculated how, if I didn't just give you a number 16.
CP theta, the sum of CP theta or negative pH.
Yes, so we're going to use this equation again. We're going to draw another line, except now we're going to start where we stopped previously. So we're going to take another line and go up at the same angle. So this is supposed to be a slope of 16 again. And we find out where that intersects our equilibrium curve. This is where it gets a little bit bizarre, right? If I wanted to calculate what the full energy balance was, this expression up here, this one, if I'm talking about the individual conversion going into reactor 2, that slope is not the same anymore because the thetas have changed. Right? Now I've got extra components in there, so that theta has changed. Ever so conveniently, though, the equilibrium curve has also changed. The net result of those two changes is they work to cancel out perfectly so that if I just keep everything based on the very first reactor, I can keep using that same line and that same slope over and over and over again. The length of that derivation takes about 3.5 pages, which I'm just going to post online. I'm not going to go over a 3.5 page derivation to show you that those two end up working the same. So the key point here is that this line has the same slope despite representing reactor 2. Has exactly the same slope, we just tack it on at the end of our previous heat exchanger. Notice what we've done. We have now increased the overall conversion. Because now, if I look at the overall conversion coming out of reactor 2, it's a little bit higher than if I just had a single reactor. So this is X overall for, no, that's really sloppy. I imagine you can write small enough to do that, but I'm going to give myself some more space here. This is XA overall after you come out of reactor 2. What's the outlet temperature for reactor 2?
Drop a vertical.
Drop a vertical right off of that second intersection. So here's our outlet for T2. So our math got a lot easier because all we need to do is calculate our energy balance for conversion of A based on the inlet conditions, as well as the equilibrium curve, this guy, based only on the equilibrium conditions of the inlet. What I had mentioned before is that the tricky part of this is that technically both of those curves are different if you were just talking about reactor 2. If you were just talking about reactor 2 and you recalculate this, your equilibrium curve would shift a little bit. Your line would also change because your inlet would be at the same place, and you'd end up with a line that looks like this. If you're just talking about the conversion in reactor 2. But now you lose this ability to kind of quickly figure out what's the overall conversion, right? Typically somebody's interested in the overall conversion because it tells you how good the total process is. This is exactly what we are not doing. This green curve is not what we are doing. We're doing a dirty trick that allows us to just focus on those inlet conditions and still learn something about the entire system. But our limitation there, because we're making those dirty tricks, is that we can only talk about overall conversions. But that's still a pretty useful number to figure out. Overall conversion is nice. I think, as we mentioned in the last class, overall conversion saves lives. How do we add the third heat exchanger? We just repeat exactly what we did before. So this third heat exchanger is going to come over horizontally to here. Then we're going to draw another line with a slope of 16 again. The outlet temperature for reactor 3, we would just drop a line down here. We get T3. And now our overall conversion has increased even further. Oh, that's going to screw stuff up. Yeah, let's not do that. XA overall coming out of reactor 3. So we've increased our conversion quite a bit, right? In this case, graphically, I don't know, we about doubled it or so. And we didn't really have to do very much math based on whatever is exactly coming out of the second reactor and the third reactor and all that kind of stuff. And we can keep adding reactions on here as much as we want. Notice, what is the overall conversion peaked at? What is the maximum value that you could get for overall conversion? If I added an infinite number of heat exchangers and reactors, I would end up getting not one, XA of equilibrium based on the inlet condition, right? No matter how many times, well, actually, unless I changed some of the temperatures along the way. If I am always fixed at going back to Ti naught, these lines are eventually going to line up right here, right? If I imagine Ti naught is my coldest temperature inside the entire system, I will never get a conversion, even if I use an infinite number of reactors, any higher than the equilibrium conversion at that temperature. Which sort of makes sense, right? If you imagine the reactor as a black box, and I said, here's what I started with, equilibrium represents the thermodynamic limit of how much of that I can convert. No matter what happens inside that black box, no matter what the catalyst is or the temperature or anything else, that equilibrium is the highest I can ever get. This is illustrating that the highest I can ever get is the equilibrium conversion at Ti naught. Unless I let one of the temperatures in there go less than Ti naught. Then I can increase it a little bit more. If, by the way, this plot is endothermic, which is what you're going to find on your project, these curves look a little bit different. So your XEQ looks this way, and your steps look that way. So this is for an endothermic reaction. And that's it. That is our dirty trick for figuring out what kind of conversion can we achieve if we have multiple reactors that are all adiabatic. That is why we derived that equation like 4 different times. It also works for any kind of a reactor. We haven't made any assumptions about what that reactor is because we have the same equation for all of those reactors. It could be any one of them. Any questions on that plot? If I gave you an actual equation, something like, I don't know, isopropanol goes to, or not isopropanol, what's a good one? N-hexane to some other kind of hexane. If I gave you actual chemicals, how would you come up with XAEQ? What piece of software would you use? EQ Calc or KEQ, either one of those. Yep, so if it's a real set of equations, that's where, or a real set of species in your reaction, you can get this strictly from thermodynamics. A convenient place to get thermodynamics is EQ Calc. If it's a fake system, like A goes to B or something like that, then you need to be given some amount of information or you can't figure out what that XEQ is. Where do I get information on XAEB? This is all coming from the problem statement. Right, you would need to know what is the theta values, what are the theta values for that inlet stream, what are the heat capacities of stuff, and what's the enthalpy of reaction that we're dealing with. So 2 important notes. These 3 steps are generally the steps that we perform if we can do something by hand, right? If we have enough information to actually solve these. Generally, that's limited to a single reaction. The reason it's limited to a single reaction is because it becomes a little bit complicated to A, figure out what delta H is, and B, isolate some sort of XA based on either the energy balance or, for that matter, the equilibrium conversion. So usually these plots are only done for single reactions if you're actually going to try to calculate something from the plot. You can create the plot after you're all done solving a multiple reaction system just to see what happened. And that's what you're going to end up doing in the project because you have multiple reactions in there. So you can't actually come up with these, but you can still create the plot when you're all done. So that will actually be a case where you can show that these two things are equivalent. So that is actually one of my notes that I have. Note 1 is for the project. Actually, it's for the blue project, so I might as well write that in blue. The green project doesn't do, wow. The green project doesn't do this. But for the blue project, what you're going to do is calculate XA overall for each reactor. And then you're going to add this to the plot. So what that's saying is that you'll be able to, in an earlier part of the project, you'll have a particular temperature and a conversion of the interesting species, and you'll be able to calculate this, the equilibrium one. You'll be able to do that based on using an isothermal reactor. The very last part of the project is to add those lines on here. In order to add the lines, you're only going to know what this point is and that point is, because I believe your reactors are going to operate at equilibrium, so you can add those points on there. Even if it doesn't operate at equilibrium, you can always simply calculate what's the outlet conditions of those reactors. Whatever those outlet conditions are can then be used to calculate whatever XA overall is. Right, so in your project, all you really need to know is what are the inlets and outlets to all of my reactors. And then you'll just be able to add these points. You don't have to calculate all the points in between there. You can just connect them by a straight line. The reason being it's fairly difficult to connect those lines if you have multiple reactions. But we know that they are connected. If you want to do it, which I believe you can, because you can actually plot overall conversion as a function of temperature inside that reactor, what you'll see is it's supposed to be straight, but it has a very small amount of curvature on it. You don't have to try to find that curvature if you don't want to. All I'm asking you to do is find out these 2 points. And then it's going to go through a reactor and you're going to add another point, or sorry, heat exchanger, you're going to add another point, figure out what the overall conversion is coming out of that reactor, and keep adding these points up. And then you can simply connect them by straight lines. So the problem on the project is somewhat straightforward in the sense that you can just keep using the same code that you used on the previous ones to figure out what those numbers are and not have to worry about recasting those equations in a way that we just saw. But you'll end up seeing a similar result as to what we're seeing right here. So that's just for the project. The other point to keep in mind is that it's always based, not it, XA overall, is always based on inlet. But it's a particular inlet, it's based on the system inlet. We never have to calculate another equilibrium curve, and we never have to calculate, we never have to calculate another energy balance, except after the first one based on the inlet conditions. And that's the easiest, or actually that's the most frequent place where you can kind of get caught up in your head. Because if I try to calculate that based on one of the other reactors, all those numbers are going to change. And like I said, that derivation exists, and it's going to get posted along with this lecture on TED. But it's kind of a pain in the neck, because it's like analyzing those reactors all by themselves, which is possible. You have all the tools to do it. You're going to do it on the project. But if you want to use this shortcut method that we're talking about here, you only have to calculate 2 of those x's, one for the energy balance based on the inlet and one for the equilibrium based on the inlet. That's the one that we're going to practice more often, right? The project is an extreme case where we can't make that simplification. Most of the time, we're going to do something like this. Most of the time, including what we're about to do. Could you help me? I have a handout here, which is a reactor system just like what we have. Don't fill it out yet. I will give you some details. I only have 90 copies of these, but I'm pretty sure there's at least 10 people out there. So pass these around, make sure everybody got a copy. I will also post these diagrams on TED. Does anybody still need one? Do you have extra? Anybody else need one? There is a reason that this sheet looks the way that it does, because you're going to see a sheet that looks like this again. And I'm not going to tell you where, but you can probably guess where you're going to see a sheet like this. This is an example of a kind of problem statement that you might have if you were in a situation where you didn't have MATLAB sitting in front of you. If you don't know what I'm talking about at this point, ask a friend. Imagine that you really did have the reaction A goes to B. You were given that particular equilibrium curve. And you were also given the particular interstage cooling system that's shown on the top of there. So you have a reactor, then a heat exchanger, reactor, heat exchanger, reactor. And you were given the following information. Pure A is fed to the system with CPA is 200 joules per mole Kelvin. You're also told that delta H, actually, let me ask you, that's a good question, is that reaction endothermic or exothermic? Exothermic, so delta H is negative. 10 to the 5th joules per mole. And Ti naught is 300 Kelvin. All the heat exchangers will cool to Ti naught. My question then would be something like, what is XA overall after you come out of reactor 3? We've only got about 5 minutes, so I will get started with this. The first thing that I would do is calculate X based on what? Energy balance or equilibrium?
Energy balance.
Energy balance, right? You have X based on equilibrium. That's the curve that I already gave you. So XA based on the energy balance is going to be equal to my heat capacity, 200, over minus delta H, which is 10 to the 5th. Did I include that negative sign last time? Double check. There should have been a negative sign back there. Times T minus Ti naught. I'll skip back right now. Oh, yeah, I got it. See that negative sign? Don't forget that negative sign. So I have a number here, right? I know what that slope is. So this is equal to 0.002 times T minus Ti naught. I will always give you numbers that have a particular meaning. 0.002, what's the distance between tick marks on your plot? The temperature tick marks. What increment? Pick a multiple of that increment. In this case, I'm going to choose 50. For every delta T is equal to 50K, right? If I put 50K inside here, my delta X is what? 0.1. What's the increment of X's on your y-axis? That is not a coincidence. So what this says is for every 2 tick marks I go over, every 50K I go up, or sorry, every 50K I go over, I go up by 0.1, which is 1 box. So
I believe that the delta T's are 25 kelvins.
that's what, yeah, that's why I said for every 2 tick marks you go over, you go up 1.
Okay.
So if for every 2 you go over, you go up 1, see if you can quickly plot out on there what your overall conversion is after reactor 3. When you get an approximate number, yell it out. About 85.
And 0.8.
Somebody else got about 80%. About a minute left. Anybody else got anything different? Or can anybody confirm those?
87.
About 87. 87, and what was the one up front? What did you, 87? Somebody got 83. Now, are you just throwing that number out there? Oh, okay. Because that's what happened last time, is people just started throwing numbers out. These all look pretty close. When I did this one and I sat down and got it, I got about 82%. So take that sheet. I'm going to post that sheet in case you've got scribbles on there that you don't want to use. Practice using that kind of a plot to figure out what the overall conversion is. You're going to practice a similar plot on your homework. But that's what interstage cooling can do for you, which is increase that overall conversion much higher than you would otherwise get out of a single reactor. Homework 3, or yes? No, if on the exam you got something close to this, I'm looking for your sketch to make sure you did the sketch correctly. If you're off by 5 or 10%, I don't mind. I will see everybody Friday. Thank you all very much.